Welcome to osmotic pressure. This is just a brief overview of osmotic pressure. It's not supposed to be an in-depth look at it. So, suppose we separate a solution and a pure solvent by a semi-permeable membrane. So, we have our solution in here in the green. We have the pure solvent outside, and down here we've got some membrane. It's semi-permeable, meaning that we're allowing the solvent but not the solute molecules to pass through. So, we can get solvent to go in or solvent to come out, but we can't get the solute to come out of our container here. So over time, our solvent flows from the pure solvent side of the membrane to the solution side of the membrane, and this increases the volume of our solution, which then of course decreases the concentration of our solute in solution. And this process is called osmosis. So because the volume of the solution is increasing, again, the concentration of our solute is decreasing. So the flow of solvent continues until either the concentration of the two sides is equal, which can't happen if one side started as pure solvent, because you can't ever get the inside to be pure solvent. Or it continues until the pressure exerted downwards by gravity equals the osmotic pressure pushing upwards. So at some point, you have a difference in height between the solution outside the beaker, or the solution outside the container, and the solution inside the container. That difference in height causes a difference in pressure pulling down on the solution. That height difference causes a pressure down here on the membrane from the inside due to gravity, but there's also osmotic pressure pushing the solvent in through the membrane. And so once those pressures become equal, then and only then will the osmosis stop. So we can calculate the osmotic pressure pi, capital pi in this case, in atmospheres. So pi is equal to capital MRT, where M is the molarity of our solution, R is the gas constant, and T is the temperature in kelvins. So that was osmotic pressure.